Given a surface that's described parametrically, we can determine the surface area by using this double integral formula. And just to give a quick idea as to where this formula comes from, let's assume that this is a very tiny portion of the surface. We'll call it S. This tiny portion's area can be approximated by looking at a tiny tangent plane to the surface at a particular point. We know the vectors that make up this plane can be considered partial respect u and partial respect v. And also recall that the area of a parallelogram can be calculated by looking at the magnitude of the cross product of the two vectors that make up that parallelogram. So the area of that tangent plane is that cross product, which can serve as an approximation for the area of the surface. And then when we add up infinitely many of those, we come up with this double integral, which essentially says that we're adding up infinitely many of those approximating areas. We've seen already that we can get the partial with respect to u vector by calculating the first partials with respect to u of each of the individual components. And similarly, we can get our partial with respect to v vector by determining the first partials with respect to v of each of those individual components. Once we have the partial with respect to u vector and the partial with respect to v vector, we'll take their cross product, and that magnitude will then become the integrand in our double integral. Now let's take a look at an example. We have the parametric equations given for a surface. Now I'll start by taking these parametric equations and expressing them as the components of a vector function, and then we'll calculate the first partial derivative of that vector function. First with respect to u. The partial with respect to u of the first component is going to be 2u. The partial with respect to u of the second component is going to be v, and the partial with respect to u of the third component is going to be 0. Similarly, the first partial with respect to v of that vector function, the partial with respect to v of the first component is 0, the partial with respect to v of the second component is u, and the partial with respect to v of the third component is going to be v to the first power. Now, let's find the cross product of partial respect u with partial respect v. To get the multiplier of our I vector, we're looking at v squared minus 0, and then we subtract the j vector times 2u times v minus 0 plus the k vector times 2u times u, which is 2u squared, minus 0. Let's now clean up this cross product just a little bit, and we see that we have v squared minus 2uv and then 2u squared as the components. We now need to calculate its magnitude, which is going to be the sum of the squares of each of the components. So we put in v squared minus 2uv and then 2u squared, and we get a radicand that factors into v squared plus 2u squared. And when we take the square root of that quantity, we get v squared plus 2u squared outside the radical, which then becomes the integrand for our surface area integral. Just as a reminder, the formula for the surface area is this cross product magnitude integrated over the domain region in the uv plane, where u goes from 0 to 1 and v goes from 0 to 2, so that region is nice and rectangular. This double integral becomes v squared plus 2u squared, which was that magnitude. Since this domain region D is rectangular, we can integrate with respect to u first or with respect to v first. So let's just pick one and go du first. We'll integrate u from 0 to 1, and then with v we're going to go from 0 to 2. And so now let's take a look at that first iteration, which is the integral from 0 to 1 of v squared plus 2u integrated with respect to u. The antiderivative of v squared with respect to u is u times v squared. The antiderivative of 2u squared with respect to u is going to be 2/3 u to the third. And we evaluate from 0 to 1, and these limits are u limits since we integrated with respect to u, which means that we plug the upper limit in for u here, and when we plug the lower limit in for u, we get 0. And all of this simplifies down to being v squared plus 2/3. And that then becomes the integrand for our second iteration, which is the integral from 0 to 2 of v squared plus 2/3 with respect to v. The antiderivative of v squared is v cubed over 3, and then we get 2/3 times v, and all of this is evaluated from 0 to 2. We plug this upper limit into the antiderivative to get 2 here and 2 here, and when we plug this lower limit into the antiderivative and subtract, of course, that's just 0. And when we simplify all of this, we end up with a surface area that is just 4 units squared.